Hey everyone! So in this video I like to go over some problems from the final review activity. And let's start with problem 4c. So we want to verify some identities. And so we're given the identity cosine of x plus y over cosine of x times sine of y is equal to cotangent of y minus tangent of x. So we want to verify this identity. In other words, we want to take one side and manipulate it and see the other side come out as a result. And so here, this left-hand side is probably the side we want to start with, because typically we want to start with the more complicated side and then try and simplify it into the friendlier version. It's harder to go in reverse. And so here, let's start with this left-hand side. We have cosine of x plus y over cosine of x times sine of y. And so one thing we can do is we can rewrite this numerator here. Maybe before I say this, I should say that there's no reducing that we can do in this fraction as is. I know there's cosines in both the numerator and denominator, and there's an x and y in both the numerator and denominator, but none of these are common factors between the numerator and the denominator. Cosine is not a multiple, it's a function, and it's taking in the input of x plus y, and this is not going to be the same as cosine of x or sine of y. So we can't do any reducing as is. We have to try and manipulate these expressions, and maybe if we see a cosine of x by itself, we can do some cancellation. If we see a sine of y by itself, maybe we can do some cancellation if they're factors, but we can't do anything like that as is. Okay, so what is the identity we can use? Well, here we have cosine of x plus y, and that's an angle sum inside the input of cosine. And so what's the identity for the cosine angle addition? Well, this is the same as cosine of the first angle, cosine of x, times cosine of the second angle, cosine of y, minus sine of the first angle times sine of the second angle. So here I'm going to make that replacement. We've got cosine of x, cosine of y, minus sine of x times sine of y. And this is all over cosine of x times sine of y. And again, we can't do any cancellation as is. The numerator is not factored, right? The numerator doesn't have a common factor in all of the terms of cosine of x or sine of y, so we can't reduce this with any of the factors in the denominator. But one thing we can do actually that might help us, we do see some common cosines of x's and common sines of y's. There's just not a full-on common factor in the numerator. One thing we can do is we can break apart the fraction. Right? So we know that a over c minus b over c, when we do the subtraction, it's just subtracting the numerators, right? A minus b over c. Right? When we just subtract fractions with common denominators, we subtract their numerators. So this is a pretty familiar equality to have, but we can also go in reverse, right? So if we have a fraction with subtraction in the numerator, we can kind of break apart that fraction across that numerator. So here this is saying that our fraction here is equivalent to, well, it's cosine of x cosine of y over cosine of x sine of y minus sine of x sine of y over cosine of x sine of y. And then now there's no addition or subtraction in the numerators of either of these fractions, and so we just see the factors of each fraction, factors of each numerator and denominator. And so now we can cancel out those common factors we see. So cosine of x can cancel out from the numerator and denominator of that first fraction. But cosine of y, sine of y, nothing happens there. Sine of x, sine of y over cosine of x, sine of y, well, there's that sine of y we can cancel out. And then we can't cancel across different fractions that are being added and subtracted. So really this is as much as we can reduce. And this first fraction comes out to be cotangent of y. And the second fraction is, what's tangent of x? Is that what we're trying to show? Yeah, so cotangent of y, tangent of x. So we've shown that the left side is very much the same as this right side. Cotangent of y, tangent of x. That was the original identity we were trying to verify. Okay, now what about the other identity, 4d? So 4d, we want to verify the identity 1 minus cosine of 2x over sine of 2x Okay, sorry, I was just checking if I was still recording. Oops, okay. It'd be very painful to realize I'm not. Okay, so 1 minus cosine of 2x over 2 sine of 2x is equal to tangent of x. We want to verify this identity, and let's again start with this left side. It's the more complicated looking side. And so here we have that same left side, and we want to come out with the expression tangent of x, or in other words, sine of x over cosine of x. And so what identities can we use here? Well, here, I know that sine of 2x, there's not much variance, not much choices to make with the replacement of sine of 2x. Sine of 2x is just equivalent to 2 times sine of x times cosine of x. And again, maybe before I make any replacements here, I also should say that, again, there's no cancellation that happens as is. I know I see this 2x and this 2x here, but those are tucked inside the inputs of sine and cosine, and those really can't be manipulated at all. We can only cancel if we see common factors, and there aren't any common factors in this numerator and the denominator. Okay, so here, I can make that replacement in the denominator. We see that 2 times sine of x times cosine of x, and that gets us closer because we see this cosine of x. Maybe we can find a way to get rid of that 2 times sine of x somehow. But now what can we do with this numerator, 1 minus cosine of 2x? Well, 1 minus cosine of 2x, there's sort of a few different ways we can rewrite this. So 1 minus cosine of 2x, this is equal to cosine squared of x minus sine squared of x. This is also equal to 2 cosine squared of x minus 1. And this is also equal to 1 minus 2 sine squared of x. And so here, is there anything we can include that might help us get rid of this factor of 2 times sine of x? Well, here I think our best bet might be to make the replacement for this expression that just involves sine, right? If I have a cosine and a sine, then I won't be able to do any factoring and cancel out that sine factor. And here it's kind of beneficial for us because we're starting with 1 take away cosine of 2x. Oh, sorry, I think, so the identity was cosine of 2x is equal to these things, not 1 minus cosine of 2x. Sorry about that. So we have 1 minus cosine of 2x, and we're going to make the replacement with 1 minus 2 sine squared of x. And so when we distribute that negative, we get minus 1 plus 2 sine squared of x over 2 sine of x cosine of x. And so here that minus 1 cancels out with that positive 1. We have 2 sine squared of x over 2 sine of x cosine of x. One of these factors of sines cancels out. And then we also have that cancellation of that common factor of 2. So we're just left with sine of x over cosine of x. That's tangent of x, just like what we wanted. So again, what we've done is we've shown that this expression, we didn't do anything, we didn't change the expression in any way. We just sort of, moved some terms around. We just, did some equivalent replacements. But we through a series of equalities, we've shown that that expression is really the same, represents the same thing as tangent of x. Okay, so for number 5, we're given a few points and some functions, and we want to ask, do these points lie on the graph of the function? So here, the first point is negative pi over 6 comma the square root of 3 over 2. Is this on the graph of f of x is equal to sine of x? And so, what does it mean for something to be on the graph of a function or an equation? It means that when you plug that point in to your function, it makes the function true. The input leads to the output. Right? So here, if I plug in negative pi over 6 for x, I should get square root of 3 over 2 for my output. So here, let's make that replacement and let's just see. We kind of have a big question mark here. Is sine of negative pi over 6, is this equal to the square root of 3 over 2? And if it is, if the input of x is equal to negative pi over 6 leads to an output of y is equal to the square root of 3 over 2, then this point truly lies on the graph of our function. And so here, maybe we can use the unit circle to help us, determine whether or not this is true. And so if we look at negative pi over 6, right, that's 30 degrees in the clockwise direction. And sine, right, it gives us the y-coordinate of this point on the unit circle. And at 30 degrees, we're dealing with this 30, 60, 90 triangle, or that side length that sine would give us. That y value would be negative 1/2. And so actually, this is not valid. So, it feels about right. Square root of 3 over 2 is one of those familiar side lengths, but it's not the right value that we would expect from plugging in negative pi over 6. So here, no. This is not on the graph. Okay, what about the next one? What about the point 1, 0 for the function h of x is equal to cosine of x? So again, 1, 0, this is a familiar point. On the unit circle, it's this point here. But that's not what we're asking. We're not asking if this is a point on the unit circle, the equation x squared plus y squared is equal to 1. We're asking if this is a point on the cosine function, the cosine graph. And so here what that means is if I plug in 1 for cosine, the input of cosine, do I get 0 out? Well, here an angle of 1, now what does that even mean? So this means 1 radian, and 1 radian is about here. And now if I look at 1 radian and I'm looking at the x value on the unit circle at 1 radian, that's definitely not 0, that's some positive value. I don't know what it is off the top of my head without a calculator, but I know it's not 0. And so again, this is not on the graph of our cosine function, right? So here maybe just to draw a quick picture, right? Cosine looks something like this, and it keeps going, right? Periodic. And what we're saying here is that this point 1, 0 is not on the graph of our cosine function. And then the last one of these types of problems I want to go over is the point pi over 4, the square root of 2 over 2. So we've got g of x is equal to sine inverse of x as our function. And so now remember that for sine inverse, it reverses the role of x and y as our inputs and outputs in our original sine function. So here the input it's not an angle anymore, it's a y value on the unit circle. And here, what we get out as an output, this is going to be an angle from the inverse sine function. Specifically an angle between negative pi over 2 and pi over 2. And so what we're saying here is, if I plug in pi over 4 into the sine inverse function, do I get the square root of 2 over 2? So actually, no, that's not the case. Here, we don't know what sine inverse of pi over 4 is. It does make sense to plug in pi over 4 into the sine inverse function because this is pi is 3.141592, and dividing that by 4 is some number less than 1. And so that is a possible y value to plug into the sine inverse function. But, this point, I think the interpretation of it is that, we're thinking of the angle pi over 4 and the y value of the square root of 2 over 2. If we were plugging this into the sine function, not the sine inverse function, it would be a valid point. But it's not a valid point on the sine inverse function. I think the interpretation of this point is sort of backwards. Okay, so now let's look at this next example. We were given a graph and we want to see which of these different equations can represent this graph. And so here, what we're doing is we're sort of imagining that we have some sine or some cosine function, and we're sort of transforming it to become this graph, right? This graph that we're given. And we want to make sure that the right transformations are applied to arrive at this graph. And so, if we have the sine function, looks something like this. Let me try and do that again. Looks something like this. Right, it has this point 0, 0. This is a sine function. And it works its way upwards to the right and downwards as we go to the left. And then it kind of oscillates. So here, when we try and imagine making some sort of matching a sine function to a graph, we kind of imagine shifting this point 0, 0 around, stretching it, and manipulating this sine function. And so here, if I'm going to move this point anywhere so it matches a point on this graph that we're given, where would that be? It might be this point here. But one thing I would notice is that, well, if we're going to sort of move this point 0, 0 to this point here, and then try and apply some other transformations to make sure that it matches this curve, well, here, this sine function goes up as it goes to the right, and this function goes down as it goes to the right from this point. And so here, not only do we need to shift this point 0, 0 to the point 2 pi over 3, comma 3, we also need to reflect this graph vertically. And so, if this is going to be a sine function, it's going to be, negative. There's going to be some coefficient based on the magnitude of the graph, but it's going to be negative sine of something, plus some quantity for the midline. So here, what is the magnitude? The magnitude is 2, right? The distance from the midline to one of the peaks. So here this is -2, negative because we've reflected it vertically. I guess I should have started with the midline. The midline is 3, so we've got a +3 here. We've kind of shifted this sine function upwards 3 units. What else is going on? There was a shift left, or a shift right actually. By how much? Well, here we've shifted to the right 2 pi over 3 units, and we've also shifted up 3 units. So we've already accounted for the shift upwards. What about the shift right? Well, how do we shift right? We subtract away from the input that value. So subtract away 2 pi over 3. And then, not only that, but we've also stretched out this function, right? So usually, these sine and cosine functions have a period of 2 pi. But here I can see that, maybe I'll use blue. To go from the peak to the lowest point, that's sort of half the period of our sine function or cosine function. Well, this distance is, that's from negative pi over 3 to 5 pi over 3. That's 6 pi over 3. In other words, that's 2 pi. That's not the period, that's half the period. Right? For us to end up back at the same sort of point along our graph, another peak, we'd have to go 2 pi further. So really the period is 4 pi. In other words, this graph has been stretched horizontally by a factor of 2. And to make our function get stretched horizontally, we need to divide that input by 2, actually. We need to multiply by 1/2. This stretches our function horizontally by a factor of 2. Since, whenever you're making these changes to the inputs, or these horizontal changes to your graph, sort of the opposite of what you expect occurs in your equation. You sort of subtract to go right, add to go left, multiply by some small number to stretch, multiply by some big number to compress. So that's what happens with the inputs of our function when we're trying to do these transformations. And so, this is one example of a sine function that does the job here. And do we see it in our picture? Yeah, so here this is one of the options that we're given. So this is a valid equation. Here we can right away see that the one above is not valid. We see this factor of 2. Everything else is valid, but that factor of 2 is incorrect. That would lead to a compression by a factor of, it would compress the graph by 1/2 horizontally. So what else? So 2 times cosine of 1/2. So the rest of the functions involve cosine. So if we had a cosine function, it might look something like this. Y is equal to cosine of x. We imagine manipulating this point around. We take this peak and move it somewhere along this graph to make sure it matches up with one of the other peaks. And so here, if I look at this graph, I would want to move that peak to this point here and apply the same stretches both horizontally and vertically. And so, again, we can see right away one of the equations that doesn't work has this factor of 2, right? We're not compressing this graph, it's getting stretched horizontally. So we're ruling that out. What else is going on here? We're moving this point from, what is this? This is 0, 1. It's getting shifted. How many units? It's getting shifted. sorry, I lost my train of thought for a moment. I'm kind of imagining stretching this graph, so it's going to get scaled by a factor of 2, and then it's going to get moved 3 units upwards. Right, so the midline again is still that same y is equal to 3. We still have that same amplitude of 2. And here, if we were to take this point 0, 1, and after we stretch vertically and we moved our graph around, here, because the graph has the same shape around this point, this peak, it's not a reflection. And so I don't need this negative factor here if I'm imagining moving my peak to this point here. And so here, this factor of 2, that sits about right. 1/2 as this factor of this input, that's right. This plus 3, that's valid too. But what about this pi over 3? So when we add pi over 3 to our input, we are shifting our graph left pi over 3 units, and that's exactly what's happening. So actually, this is a valid equation for the graph too. Now in the next example, we're dealing with this cosine function again. We still have that same input coefficient of 1/2. But now here this is telling us, shift this graph right 5 pi over 3 units. And then, we saw that same midline. We saw that same amplitude. So it's saying shift the graph 5 pi over 3 units and then reflect it. So here it's kind of like taking this point and shifting it. How should I say this? It's kind of like we took this point and we reflected the graph. So now we're not looking at a peak, but we're looking kind of like at a low point. And then we're shifting this low point to this point here, or this point at 5 pi over 3. And so actually this equation is valid too. Okay, so I don't know if I explained that last one the best, but yeah, I definitely encourage you to pause and stare at this one for a little while and convince yourself that it's valid, that really I can get to this point by taking our peak, and vertically reflecting it so that it's not a peak, but it's sort of the low point, and then the shifts and the stretches are done so that that low point ends up here. So for this next example, let's graph the polar equation r is equal to 4 times sine of 3 theta. And let's make a table of points, theta and r, so that we can plot these points and sketch the curve that runs through them. And so here, let's use some values between 0 and pi to start with, and maybe we can pick some values that are nice when we multiply them by 3. In other words, angles that when we multiply them by 3, we know how to evaluate sine at such an angle. And so one such angle is pi over 6, right? If I multiply this by 3, actually let's start with 0, 0, or 0 for theta. So here we've got 4 times sine of 3 times 0. Well, sine of 3 times 0 is still sine of 0, and that's 0 also. So 0 times 4 is 0. We've got 4 times sine of 3 times pi over 6 for the next example. Well, this is sine of pi over 2, right? 3 times pi over 6 is pi over 2. And sine of pi over 2, that's just 1. So this comes out to be 4. If we choose the next multiple of pi over 6, let's do pi over 3. 4 times sine of 3 times pi over 3. Well, sine of 3 times pi over 3, that's sine of pi. And sine of pi is also 0. So 0 times 4 is 0. Now let's do pi over 2. 4 times sine of 3 times pi over 2, that's 3 pi over 2. Sine of 3 pi over 2, that's negative 1. So this is negative 4. We've got 2 pi over 3. This is 4 times sine of 3 times 2 pi over 3, which is the sine of 2 pi, that's 0. And then 5 pi over 6, 4 times sine of 3 times 5 pi over 6. Well, 3 times 5 pi over 6, that's 5 pi over 2. In other words, that's pi over 2 past 2 pi. And that gives us 1 from sine. And then we multiply that by 4 and we get 4. And we can kind of see the pattern here. We're getting 0, 4, 0, negative 4, so on and so on. So when we plug in pi, we end up back with 0. Okay, so how do we plot these points in polar coordinates? Well, here we're just going to go to this angle and plot the point this many units away from the origin. So here, the point 0, 0, it's saying go to an angle of 0 and then plot the point 0 units away from the origin. Well, 0 units away from the origin is at the origin itself. And then at pi over 6, out here, we're going to be 4 units away from the origin. And then at pi over 3, we're going to be 0 units away from the origin, so we're back at where we started. So here, maybe I'll just start sketching this curve. It looks something like this. Then pi over 2, we're at the point where we have a -4 value away from the origin. So here, at this angle, pi over 2, I'm going to travel 4 units in the opposite direction, so out here. And so here we end up with this curve, and then at, 2 pi over 3, back at the point 0, and we can kind of see that, the idea is that as we're sort of traversing this angle, from pi over 2 to 2 pi over 3, we're going to start plugging in opposite values. The values are going to be negative, or the outputs are going to be negative, but they're going to get smaller and smaller towards 0. And then here, 5 pi over 6, we're at +4. So here, we start getting larger and larger values until we get to +4, and then we start going back. Right? At pi, we're getting 0, and then we start traversing this curve and start repeating itself. But one thing I want you to notice is that, for example, at 7 pi over 6, we get a -4 as an output, right? So we plug in 7 pi over 6. This is 4 times sine of 3 times 7 pi over 6. This is equal to 4 times sine of 7 pi over 2. And on the unit circle, 7 pi over 2. Right, so here this is 4 pi over 2, right, just 2 pi, 5 pi over 2, 6 pi over 2, 7 pi over 2. This is going to give us -1 from sine, so it's going to be -4. And so here, the point we see is that at as we go to 7 pi over 6, we're 4 units in the opposite direction, so we're back out here. But now this point we're looking at is not pi over 6 comma 4, it's 7 pi over 6 comma -4. Okay, but anyways, this graph just repeats itself as we go all the way to 2 pi, and then it just continues to repeat itself even after that. But this is the graph of our curve. So in this next problem, we want to convert some polar equations to rectangular equations, and vice versa, rectangular equations to polar equations. And so let's start with the equation r is equal to 1 plus 2 times cosine of theta. And so the main ways we have to translate between polar equations and rectangular equations, or Cartesian equations, are the idea is that x is equal to, this is r cosine of theta, y is equal to r times sine of theta, and then we also have, x squared plus y squared is equal to r squared. And this can all be seen from the triangle, right? If I have a point here, this is r comma theta, this distance is r, and this angle is theta. And we're trying to see what this point would be, in terms of x and y. Well, that would be this distance here and this distance here. And it's just true that if we take sine of theta, well, we get y over r. Right, so here it's sine of theta is equal to y over r. And if we multiply both sides by r, we get the equation here, the relationship y is equal to r sine of theta. And we could do the same thing for x. Right, cosine of theta is equal to x over r. Multiplying both sides by r gives us this relationship here. And then this relationship, x squared plus y squared is equal to r squared, well, this is just the Pythagorean theorem. Right, so this is how we can go back and forth between x's and y's and r's and thetas. And when we have this equation in polar coordinates, to convert it into a rectangular equation, or a Cartesian equation, we just want to use these ways of translating so that we end up with a new equation that does not have r's or thetas anymore. And so here, one thing I can imagine doing is I can imagine, I see this cosine of theta, and I would prefer for that cosine to have a factor of r with it. I also see this r, and I would rather have this r be an r squared, so that I can convert it to an x squared plus y squared. And so if I do that, if I multiply throughout this equation by r, I get r squared is equal to r plus 2r cosine of theta. And we can make some translations here. R squared, that's the same as x squared plus y squared. And then here we have this is equal to r, and we don't have any translation for that as is, 2 times, well, here this is just 2 times x. R cosine of theta is just x. Now how do we get r? Well, if r squared is equal to x squared plus y squared, r is going to be plus or minus. So r is equal to, here, plus or minus the square root of x squared plus y squared. And so here, I'm just going to rewrite this as x squared plus y squared is equal to the square root of x squared plus y squared plus 2x. So that's one form of an equation that's almost equivalent to this form, or this original polar equation. It's sort of one piece of it, and we would get the other piece if we also included the equation where we made the replacement r is equal to minus square root of x squared plus y squared. Okay, so that's one conversion we can do. Here, let's do another example. Let's do D, where we have x squared plus y squared is equal to 2xy. And so we can make the same conversions right here. X squared plus y squared, that's just r squared. So we've got r squared is equal to 2 times x times y. So x, we said that's the same as r times cosine of theta. And y is the same as r squared, or r times sine of theta. So this is r to the 4th is equal to 2r squared cosine of theta sine of theta. Now we don't have to do any more. This is fine enough for us as is. So in this next example, in problem 11, we're given the equation x is equal to e to the 4t minus 5 and y is equal to e to the 8t. So here these are parametric equations, and we're asked to eliminate the parameter and use this to graph the equation, both the Cartesian equation that comes from eliminating the parameter and then the parametric equation as well. So one way we can eliminate the parameter is, we can try and get that value, that variable t by itself, and then plug it into the other equation for that t. Here I see that these equations, the t part, they're very closely related, right? E to the 4t, this is almost the same as e to the 8t. This is not true, a true equation as is, but if I squared it, it would be true, right? E to the 4t, if I square it, right, multiplying something to itself, or multiplying two powers with the same base, it just amounts to adding their exponents, right? This is 4t plus 4t. In other words, this is e to the 8t. So, these two these two equations we have for x and y, they're very, very similar. They're almost, they're very related to one another. Let me isolate that e to the 4t and see what I can do to get rid of these t variables. So here we've got x is, if we add both sides by 5 to our x equation, we get x plus 5 is equal to e to the 4t. And here I know that e to the 8t, we said that this is e to the 4t squared. Right, so what we're saying is that y is the same as e to the 4t squared, but e to the 4t is the same as x plus 5. So really, y is the same as x plus 5 squared. And so if we graph this equation, this rectangular equation or Cartesian equation, this is a parabola. And this is one that's shifted to the left 5 units, right? So here it looks something like this. This is the graph of y is equal to x plus 5 squared. Now, what's the graph of our parametric equation here? Now, what's the graph of these equations? Well, notice that e to the 4t, this is non-negative. It's also never 0. And so here, if I'm subtracting 5 away from x, and I know that e to the 4t, sorry, if I'm subtracting away 5 away from e to the 4t, well, I know that the smallest this is going to be it's going to be more than negative 5. Right, so here, this is going to be, it's never going to be negative. It's always going to be greater than 0. And so if I subtract away 5, well, this is only going to add on to negative 5, never subtract away. And so x is only going to be to the right side of negative 5. And then here, y, right, it's always positive, right? This is always positive. What we end up getting as a graph of our parametric equation is only this portion of the graph here. Right, so there are many times when you're dealing with parametric equations that, and you're trying to eliminate the parameter, the graphs you have of your original parametric equation and the eliminated parameter equation, they're not always equivalent. Sometimes there's some restriction here. And so that's the case in this example. So in this next problem, problem 15, we want to find the angle between the two vectors u is equal to, and I guess I'll use blue here like I have in the past for vectors. U is equal to the vector 3, negative 2, and v is the vector 1, 2. And so pictorially, if I kind of imagine drawing these vectors out, maybe I'll place them at the center at the origin. Right, the positions of vectors don't really matter, so I can plot them wherever I want. Let me just draw them just to give us some picture in mind of what we're really doing. So 3, negative 2, that's saying that we've got a horizontal component of 3 and a vertical component of negative 2. So here our vector looks something like this. This is u. And then 1, 2, our vector looks something like this. This is our vector v. And we're trying to find this angle. And so the angles between two vectors, they can be found by using the dot product. And so the dot product has two different definitions. U dot v is equal to a1 times a2 plus b1 times b2, where here a1 and a2 are the horizontal components of our vectors, and b1 and b2 are the vertical components of our vectors. So this is a nice way to compute the dot product, but actually this is equivalent to the magnitude of v times the magnitude of u times cosine of the angle between these two vectors. And so here we can compute the dot product in kind of a convenient way, and then try and relate it to this expression here to find the angle. And so here u dot v, if we compute it this way, approach number 1, what we get is that u dot v, well, this is equal to 3 times 1, that's 3, plus negative 2 times 2, that's negative 4. So this is negative 1. And then here, if we, now we know what u dot v is equal to. And so here we can use this second approach to find cosine of theta, to find theta. And so here we need to figure out the magnitude of u and the magnitude of v, in other words, the lengths of the vectors, and this is just done by using the Pythagorean theorem, right? This is a right triangle, this is a right triangle. This u triangle, well, it has side lengths, leg lengths 3 and 1. So if I square 3 and I square 1, add them together, that's going to be like a squared plus b squared is equal to c squared, and I would take the square root of both sides. So this is the square root of 9 plus 1, square root of 10. That's this distance here for u. Now what about for v? What's the length of v? Well, here we could do the same thing, but with the side lengths 1 and 2, right? This is 1 squared plus 2 squared. That's 5. So the magnitude of v is the square root of 5. So this is negative 1 is equal to the square root of 5 times the square root of 10, which is equal to, actually no, I think I computed this wrong. Sorry, this is square root, this is the magnitude of u is not square root of 3 squared plus 1 squared. Here, the vertical component was negative 2, right? So this is going to be 3 squared plus 2 squared. In other words, the square root of 13. So this is magnitude of v is the square root of 13. And this is times cosine of theta. And so if we get that cosine of theta isolated, we have negative 1 over the square root of 5 times the square root of 13. We can use inverse trig now to figure out the value of theta, right? So, theta, we're looking for an angle between two vectors. It's going to be, the most they are going to be away from one another is going to be 180 degrees. And that's great because cosine inverse is only going to give us an angle between 0 and 180 degrees. So there's no issue there. We don't have to worry too much like we usually do when it comes to inverse trig and finding angles. So here this is going to give us an angle, and it gives us about 97 degrees. And the problem we're asked to find the angle to the nearest degree, it comes out to 97.1. So really this to the nearest degree is 97 degrees. And so that's this angle here between these two vectors, and that makes sense, right? This is 97 degrees. Looks like it's a little bit more than a right angle. Okay, so this next problem we have is where there's this jet flying through the sky and there's some wind blowing in a slightly different direction, and we want to use our knowledge about the direction of the jet and the direction of the wind to determine what the true direction and speed will be of this jet after influence by the wind. And so here, we have that this wind, maybe I'll label this vector u. It's got a magnitude of 55 miles per hour. We can use the magnitude of our vector to represent the speed of the wind. And then here it's also got a direction 30 degrees east of north, right? So 30 degrees shy from north, so I can think of that as also 60 degrees in standard position. Okay, so this is telling us that if we want to find this vector corresponding to the wind in component form, then here recall that if I have a vector, so vector v, this component form just means find the horizontal displacement and the vertical displacement of this vector, and we've been labeling that A and B. This is the same thing as what we've done for polar coordinates. A is equal to the magnitude of v times cosine of theta, so this is our angle theta here, and B is equal to the magnitude of v times sine of theta, right? If I take cosine of theta, we get A over the length of the vector. Shuffling this around gives us A is equal to the magnitude of v times cosine of theta, and then here if I take sine of our angle, then we get b over the magnitude of v, and so rearranging that equation gives us b times the magnitude of v sine of theta. And so this tells us that v, our vector, it's really in component form, it's the same as a, which is the magnitude of v cosine of theta. Sometimes we'll write this with our sort of nice unit vectors, our length 1 vectors in the horizontal and vertical direction. And so in this example, we have that v is equal to, well, the magnitude of v is the length of the vector, and here that's the speed of the wind in this case. If we're talking about, actually I should use, maybe I'll label this wind vector v since I've already started writing it out this way. This is cosine of 60 degrees times I plus 55, right, the magnitude or length of our wind vector times sine of 60 degrees times j. And so cosine of 60 degrees, that's 1/2. Right, here's our 60 degree angle, and then here it's the short side length, it's 1/2. So here this is equal to 55 over 2, right? 55 times 1/2 I plus, well, sine will give us, sine of 60 degrees will give us square root of 3 over 2, so this is 55 square root of 3 over 2 times j. So this is our wind vector. And by the same reasoning, right, so here the jet is traveling 675 miles per hour. It's traveling 45 degrees east of north. Well, here we can say that if I call my plane vector u, then u is equal to the magnitude of u times cosine of our angle theta times I plus the magnitude of our vector times sine of our angle theta times j. And then this gives us, well, here, the magnitude of our vector is 765. Cosine of 45 degrees is the square root of 2 over 2. Then we have the magnitude of our plane times sine of 45 degrees, that's the square root of 2 over 2. This is our component form for our plane vector before it's influenced by the wind. And then if we want the vector that describes the plane after influenced by the wind, well, we just add these two vectors together, u and v. And so this is equal to, well, we add their horizontal components, 55 plus 765 square root 2 over 2 times I, then plus 55 square root 3 plus 765 square root 2 over 2 times j. And so this is the new vector telling us the true velocity of our plane. And so if we want the true speed and the true direction, what we need to do is we need to find the magnitude of this vector. In other words, we need to find the magnitude of u plus v. This is equal to the square root of here this quantity squared plus this quantity squared, right? The horizontal and vertical displacement squared. So 55 square root 3 plus 765 square root 2 over 2 squared. And when we compute this, this gives us approximately 818.25, and this will be miles per hour. And this kind of makes sense, right? So the wind is blowing somewhat, pretty close to the direction of the actual direction of the plane. And so, a lot of the speed offered by the wind is going to push that plane, and if it's going to increase by quite a few miles per hour. Now, what about the direction? Well, here, this is the vertical coordinate, the vertical displacement of our true velocity vector for our plane, and then here, this is the horizontal displacement of our velocity vector for the plane. And so if we take, here, if we imagine that vector, it might look something like this. Right, so we have this value here, and we have this value here, the horizontal and vertical displacement of the plane, and we want the direction. Well, the idea is that if we take inverse tangent of b over a, right, the vertical displacement over the horizontal displacement of our vector, we'll get this angle. As long as this vector is, heading towards the right, we don't have to do anything different. If it's heading to the left, we had to add 180 degrees to this resulting angle from inverse tangent. But that's not the case here. It's heading to the right, and so this is approximately equal to, when we take inverse tangent of this vertical displacement divided by this horizontal displacement, we get roughly 46 degrees. So 45.99, we get 46 degrees.